This is Chapter 9, Asteroids, Comets, and Dwarf Planets, their nature, orbits, and impacts. So Chapter 9 is kind of the miscellaneous of our solar system. Those little bits and pieces of ice and dust and dirt that make up what's left of our solar system. Our goals in 9.1 are to look at what are asteroids like, why is there an asteroid belt, and how are meteorites related to asteroids. Here's a great picture of an asteroid called Itokawa, photographed by one of their missions. It landed on the surface and actually brought back a very, very small sample of the asteroid to Earth. It's fairly easy to discover asteroids, and that's why some asteroids have been named after modern and even amateur astronomers. They leave trails in long exposure pictures. The stars might remain stationary, but they are moving relative to the stars in the background. We think asteroids are rocky leftovers of the initial planet forming, all the planets forming. The largest one that we've found is called Ceres. It's about 600 miles or 1,000 kilometers in diameter. So far, we've cataloged 150,000 asteroids, and there are probably many, many more that need to be identified. There are more small asteroids than there are large asteroids. And even all the asteroid mass put together wouldn't add up to even a small terrestrial planet. So even though there are a lot of them, they're very small in size compared to a planet. These are photographs of some asteroids that have very unusual shapes, but in fact asteroids have all different kinds of shapes. Shapes are one thing, but another common feature is that they all have impact craters. This is a picture, two different views of the asteroid Vesta, and as you can see, it has a very wide equatorial diameter, but we think it might be because of a very large impact that something else hit it near its south pole. So again, asteroids can be pretty much any shape and size. Asteroids can also have their own moons, as we can see here with asteroid Ida. The tiny moon off to the right there is called Dactyl. So asteroids can be large enough to capture smaller fragments of rock, and of course if they orbit that asteroid, they are called moons, natural satellites. So why is there an asteroid belt? Well, here's another example of an asteroid. It's called Matilda. It's photographed by the NEAR spacecraft, which made several near passes of asteroids. This is a pretty good view of where the asteroids are in two different locations. Most asteroids orbit between Mars and Jupiter. As you can see, that's called the main asteroid belt. But then there's also something called the Trojan asteroid belt. And as you see here with the orange circle, those asteroids are mainly in line with Jupiter's orbit. So orbits of near-Earth asteroids sometimes cross Earth's orbit. They wander out of their path, and sometimes we experience their passage. Asteroids in orbital resonance with Jupiter sometimes experience little nudges in their orbit, which can throw them off, and so that's why we might have some of these asteroids approaching us. Eventually the nudges move asteroids out of their orbits, and it leaves gaps in that belt. So we have these rocky planetesimals between Mars and Jupiter that never actually accreted or collected into a planet. And then Jupiter's gravity, through the influence of these resonances, in other words, the gravitational pull of Jupiter, stirred up the asteroid orbits and prevented their accretion into an orbit as well. So we have two parts of our solar system that have these asteroids, but 4.5 billion years ago or whenever, they never really formed a planet. Here's a picture of something that we've found on the surface of the Earth. It's a meteorite, and we're going to look at how meteorites are related to asteroids. Most meteorites are pieces of asteroids, and we can actually tell what the composition then of some asteroids are if we find a meteorite. So a meteorite is a rock from space that falls through the Earth's atmosphere. In other words, it's something we would pick up on the surface of Earth. A meteor is the bright trail left by a meteorite. So a meteor is something we see up in the sky. The meteorite is the actual rock sample. There are two meteorite types. One is called primitive, which means it probably was unchanged in composition since it first formed with the solar system. And then there are some called processed, which are younger and they've experienced volcanism or differentiation. So something happened to them or they formed at a much younger time. Primitive meteorites consist of two types, as you can see here, stony primitive and carbon-rich primitive. The composition of the meteorite is somewhat different. Their appearance is different, and of course their composition is different. Processed meteorites are of two types as well. We have metal-rich processed and rocky processed. So again, as you can see in these sawed-off cross-sections of the meteorites, they also have different compositions. There's a few meteorites that have apparently arrived on Earth from the Moon and Mars. In other words, the impact of another object into the surface of one of those two objects, such as the Moon and Mars, splashed up material. They reached escape velocity of the Moon or Mars and actually fell into Earth's atmosphere. So we have some samples of moon rock and Martian rock here on Earth that we were able to just pick up off the surface. Scientists are pretty sure these are from these two places, since they're very, very different from asteroid fragments. So it's a pretty cheap way to acquire moon rock and Mars rocks. So what are asteroids like? Well, they're rocky leftovers left from the era of planet formation. And why is there an asteroid belt? Well, because of these orbital vibrations or resonances with Jupiter that prevented the rocky planetesimals between Jupiter and Mars from forming a planet. So it's almost like there was this huge amount of gravitational pull that Jupiter was influencing these pieces that could have formed a planet but didn't. How are meteorites related to asteroids? Well, most meteorites are pieces of asteroids. There are primitive meteorites and there are processed meteorites. Those are the two types. So in 9.2 we'll look at comets. How did comets get their tails and where do comets come from? This is comet Hyakutake that passed by the Earth. And we were able to get some very, very good pictures of it. Comets are formed beyond the frost line, and so they are made of icy particles. Kind of like asteroids are made of rock material, they're made of ice. The nucleus of a comet is like a dirty snowball. Most comets don't have a tail, as we'll see in a little while why. And most comets remain perpetually frozen in the outer solar system. They don't approach the Earth, they just remain stranded out there. And only comets that enter the inner solar system grow tails, because as they approach the sun, they start to burn up. So here's the nucleus of a comet. Very, very small, again called a dirty snowball. Source of material for the comet's tail is maybe bits and pieces of asteroid material plus all of this ice. So there's the nucleus. There's something called a coma, which is this blasting away of the material, forming escaping gas. There's what's called a dust tail and a plasma tail. The coma is the atmosphere that comes from heating the nucleus of the comet, and the plasma tail is gas escaping from the coma. The dust tail is pushed away by the sun, by photons that the sun is giving off. So every comet, as it approaches the sun, actually appears to have two tails. The tail actually grows the closer it gets to the sun. So as you can see with this highly elliptical orbit of a comet, as the comet approaches the sun, it starts to move around the sun, and notice that it's in a clockwise direction, which is certainly possible with a comet. Its dust tail is being pushed away by sunlight, and the plasma tail is being swept back by solar wind. Here is a picture of Comet Tempel. Something hit the surface on July 4th of 2005, and by doing so, we were able to study what happened as the spacecraft, or the projectile, hit the surface. So comets eject small particles that follow the comet around in its orbit and cause meteor showers when the Earth crosses the comet's orbit. So we've pretty well been able to predict when that occurs. We know when we pass through these comet tails, and we know exactly when these particular meteor showers will occur. This is an example taken in Australia in 2001 of the Leonid meteor shower. The meteors appear sort of coming out of the same direction or the same place in the night sky, as if the Earth is moving into that area, that piece of tail material, kind of like a car going through a rainstorm. So where do comets come from? Well, there's actually two places. Most of them remain far away from us in the Oort cloud, which is this huge spherical cloud surrounding our sun, out to about 50,000 AUs. But there's also the Kuiper belt, which is somewhat closer, between 30 and 100 AUs, and that would make it somewhere near or outside of Pluto's orbit. So that's usually where comets reside. So Kuiper belt comets were formed in the Kuiper belt, a fairly flat plane aligned with the other planets in their orbit and orbiting in the same direction as the planets. The Oort cloud comets are very, very different. They are spherically distributed around the sun, and they orbit in any direction at any angle. So how do comets get their tails? Well, comets are like dirty snowballs, and of course they burn up as they approach the sun. They grow their tails as they approach because of the solar wind and the photons heating up the nucleus and pushing material away from the nucleus. Comets come from the Kuiper belt and the Oort cloud mainly. All right, Pluto, lone dog no more. It's been kind of kicked out of the planetary system for various reasons. So we'll look at how big a comet can be and what are Pluto and other large objects of the Kuiper belt like. Here's some pictures of some objects out there in our solar system. I think the most interesting one is Ceres, the asteroid, in the bottom left, compared to something like Charon, which is a moon orbiting Pluto. Pluto's orbit is very unusual compared to the other 8 planets. It is tilted at a 17-degree angle, and it's very elliptical, so elliptical that Pluto actually orbits inside Neptune's orbit for about 20 years. Pluto's much smaller than the other 8 planets. It's not a gas giant like the Jovians. It has an icy composition like a comet. It's very elliptical, very inclined orbit, and it really seems to have more in common with comets than it does with the other 8 planets. In the summer of 2005, we discovered Eris, which is an ice ball even larger than Pluto. So again, Pluto seems to be sort of the oddball in our solar system. And there are many other icy bodies. Pluto has this elliptical inclined orbit, most of the time beyond Neptune, and the largest of these are comparable in size to Earth's moon. So let's look at the Kuiper Belt objects. They're large icy objects. They have orbits similar to the smaller objects in the Kuiper Belt that have actually become comets. So are they very large comets or very small planets? I guess that's a question to ask. In 2006, the IAU decided to call Pluto and objects like it dwarf planets because they really didn't fit the structure of the solar system. The four terrestrial planets, then the four Jovian planets, they were a completely different classification. So what are Pluto and other large objects of the Kuiper Belt like? Well, this is the most recent photograph of Pluto. And as you can see, there are features there that are recognizable. And so we have, since the summer of 2015, been able to get much more information about Pluto. Its largest moon, Charon, is nearly as large as Pluto. It's very, very cold, being 39 AUs away from the sun. But Pluto has a very thin nitrogen atmosphere that refreezes. So actually the surface does have ice of a different nature than we'd expect. Here's the Hubble Space Telescope view of Pluto with some of its moons. So how big can a comet be? Well, the Kuiper Belt from which the comets come from contain objects as large as Pluto, but Pluto and the other dwarf planets are more like large comets than they are major planets. So what are Pluto and other large objects of the Kuiper Belt like? Well, they're large objects, they have tilted elliptical orbits, and they basically have icy compositions like those of comets. So Pluto and these other objects out in the Kuiper Belt are very much like the Kuiper Belt comets. And in 9.4 we look at cosmic collisions, impacts on Earth. Did an impact kill the dinosaurs? How great was that impact risk, or is the impact risk? And how do the Jovian planets affect impact rates and life on Earth? The big question is, did an impact kill the dinosaurs? In other words, was something approaching the Earth that crashed, that caused all sorts of climate change? Well, small objects impact all of the planets every day. Evidence suggests that large impacts are also still occurring, such as the impact of comet Shoemaker-Levy 9 into Jupiter in 1994. Here's a sequence of pictures as the comet was approaching Jupiter. It caused a string of violent impacts, and it reminded us that we could have the same thing happening on Earth at some point, either with a comet or an asteroid or a very large meteor. But Jupiter being as large as it is, the comet was torn apart due to its gravitational pull. Here's a crater chain on Callisto that probably came from a comet that was broken up into smaller pieces. Here's an impact plume from a piece of Shoemaker-Levy 9 that rose up above Jupiter's surface. So as it went, when it hit the quote surface unquote of Jupiter, it actually caused a plume, a cloud. Here's dusty debris at one of the impact sites. You can see that kind of crescent-shaped cloud to the lower left of where the comet hit. And this is just an artist's rendering of what we might have seen if we were on the surface of Io looking back at Jupiter. Those little splotches that you see going from upper right to lower left are more impact sites of the comet into the surface of Jupiter. And here's an infrared photo showing the glow of some kind of fireball that erupted from the impact of Shoemaker-Levy 9. So, what about the fossil record? Well, it does show occasional large dips in the diversity of species. We call those mass extinctions. The most recent one appeared to be 65 million years ago, and that appears to be the time when dinosaurs became extinct. There's an element called iridium, which is very rare in Earth's surface rocks, but we can find it in meteorites. So these two gentlemen found a layer, a very thin layer of iridium, and figuring out the ages of the rocks before and after this deposition, they estimated the iridium layer to be about 65 million years old, probably from a meteorite impact. In other words, when the meteorite broke up, the iridium was deposited within these rocks, and they've been able to age date them. So all dinosaur fossils are found below this layer. No dinosaur fossils are found above this layer, as you can see in the photograph here. It's a very thin layer of this element, iridium. So it would kind of indicate that something happened about 65 million years ago that killed off the dinosaurs. And iridium is this trace element found in meteorite material. So a meteorite about 10 kilometers in size would send large amounts of debris into the atmosphere. That debris would reduce the amount of sunlight, forcing the Earth to be cooler, and that could have caused mass extinction. Here's where we think that meteor may have hit. There's a place off the coast of Mexico that we have evidence of a crater off the Yucatan Peninsula, and that may have hit approximately 65 million years ago. So, comet or asteroid approaches about 10 kilometers in diameter and hits the surface of the Earth, throws material into the atmosphere, and pretty much wipes out the existence of a major species of animal. So the impact of such a large object would have ejected debris pretty high into the atmosphere, and that would, of course, cloud or shield the Earth from sunlight. So we know asteroids and comets have hit Earth, and major impact is only a matter of time. The size would, the larger the size, obviously, the more rare it would be. So major impacts are very rare, but extinction level events occur over millions of years, and major damage might occur in tens to hundreds of years. Here's an asteroid that apparently detonated over Chelyabinsk, Russia in February of 2013. It released a lot of energy, caused a lot of damage. This is an example of something that disintegrated very close to the surface of the Earth. It just pretty much self-destructed and caused this terrible damage in Tunguska, Siberia in 1908, where all the trees were laid flat in sort of a radial direction, kind of like spokes of a wheel, out from where the impact site was. Here's another example here in the United States, Meteor Crater, Arizona, where we estimate about 50,000 years ago, a 50-meter object hit the surface of the Earth. So as you can see by the graph, the frequency of impacts happen quite often, the small impacts. The larger impacts occur not as often. So you get kind of a line going from upper left to lower right. The largest objects might create mass extinctions. In the middle there might cause tsunamis, widespread devastation, and climate change. And the ones in the upper left might cause some sort of atmospheric explosion or a small crater if it actually reached the Earth's surface. So, asteroids. When will it occur? Well, we don't know yet, but with maybe better and more advanced technology, we might be able to affect the outcome of an asteroid or a comet approaching us. We might actually deflect it, move it away from us as we're moving in our orbits. But breaking a big asteroid into a bunch of little asteroids is not going to help. That'll just create more impact sites. We have satellites in orbit, telescopes in orbit that are attempting to detect asteroids and comets that might approach us, and It seems like every few weeks or so we hear about one that is doing a close approach. But so far, none has made any serious damage, created any serious damage, or has even approached the Earth to the extent that we have to be worried yet. So how do Jovian planets affect impact rates and life on Earth? Well, the Jovian planets have a tremendous amount of influence because they can affect anything approaching us from the Kuiper Belt or the Oort cloud. So they can either deflect an object or actually turn it into the Earth. Jupiter has directed some comets toward Earth, but has ejected many more into the Oort cloud. So fortunately for us, Jupiter, as large a planet as it is, has probably saved us many, many times. We pretty much know that impacts can extinguish life. But were they necessary for life as we know it? That's a good question. Was Jupiter necessary for life on Earth? In other words, did Jupiter actually deflect a lot of asteroids that may have hit the Earth otherwise? Those are two very good questions. So, did an impact kill the dinosaurs? Well, we have this iridium layer just above the dinosaur fossils that suggests there was an impact about 65 million years ago. And we do have evidence of a crater that dates to about that age, large enough to do the damage we think it did. How great is the impact risk? Well, large impacts do happen, but they're rare, thank goodness. They can cause major extinctions about every 100 million years. It's certainly possible. And how do Jovian planets affect the impact rates? Well, Jovian planets sometimes deflect comets toward Earth, but they send many, many more out to the Oort cloud.